Welcome to the Deep Dive, your shortcut to getting up to speed. We sift through the sources so you get the core knowledge you need right now.
And today, we're tackling something big in the Java world, Project Loom. It's really rewriting the playbook for concurrency. If you're building any kind of back-end system, you need to know about this. It's probably one of the biggest shifts in, the last decade.
Absolutely. I mean, modern apps, they need to handle just massive amounts of concurrent users,
Yeah.
lots of I/O waiting, and the old Java threading model, well, it just couldn't keep up. It hit a wall.
A hard wall.
Yeah. So today we're doing a deep dive into the three main parts of this: virtual threads, structured concurrency, and scoped values. We want you to understand how they work and, maybe more importantly, why they make such a difference for performance and just, developer sanity.
Exactly. And maybe to frame it, before Java 21 really landed this stuff, the limits on concurrency, they were pretty much set by the operating system. You couldn't really escape that. Loom basically pulls that control back into the JVM, and that changes fundamentally how you even think about concurrent tasks.
Okay, so let's unpack that.
Yeah.
Before we get all excited about the new stuff, maybe we should quickly touch on why the old way, the platform threads, was such a problem. What was the core limitation there?
Well, the bottleneck was fundamentally about scarcity and cost. Platform threads, under the hood, they're really just thin wrappers around the operating system's threads.
Okay, so the OS is doing the real work.
Exactly. And every single time your Java application asked for a new thread, the OS had to step in, do an expensive system call, allocate resources. It wasn't cheap.
And that resource allocation, that was the killer part, wasn't it? The memory?
Oh, yeah, huge. You were often looking at like a megabyte of memory per thread, and critically, that was off the Java heap.
Off heap, right?
And it was a fixed size. You couldn't resize it. So, imagine you've got 100,000 users hitting your service simultaneously. If each needs a thread, well, you run out of memory, or just grind the system to a halt really fast. The OS itself puts the brakes on.
Yeah, and developers obviously knew this. We spent years trying to work around it. The first attempt was just awful, right? The thread per task model.
Oh, terrible. Just creating and throwing away these expensive OS threads constantly. Massive, massive waste.
So that led to the executor service, I think back in Java 5. I was supposed to fix the waste by reusing threads.
Right, pooling. Create a pool of these expensive platform threads, submit your tasks, reuse the threads. It definitely helped with the creation destruction overhead,
Huh.
but it created its own set of problems, two big ones, really.
Okay, what's the first? Blocking, right. Yeah, that kind of defeats the point of reuse.
Exactly. If a thread from that pool takes a task, and that task needs to, say, wait for a database query or a network call, that thread just sits there, blocked. It's holding on to that valuable OS thread, that megabyte of memory, and it can't do any other work from the queue.
So your expensive pool isn't actually working efficiently if there's I/O involved.
Precisely. Its efficiency just tanks the moment you interact with anything outside the CPU.
And the second problem, oh, the nightmare of ThreadLocals. Every experienced Java dev probably shudders hearing that.
Yeah. If you've ever chased a bug for days that only showed up under load or on one specific server, you've likely felt the pain of ThreadLocal leakage.
Explain that quick.
So ThreadLocal lets you associate some data with the current thread, useful sometimes. But in a pooled executor, if your task sets a ThreadLocal value and then forgets to explicitly clean it up using remove before finishing, that value stays attached to the thread when it goes back into the pool. The next task that picks up that same thread, suddenly it sees the leftover data from a completely unrelated previous request.
Ghost data, leading to just bizarre, hard-to-reproduce bugs.
Exactly. State pollution across requests. Horrible to debug.
And then there were the other workarounds, like async programming frameworks, vert.x, things like that. They helped with resource use, but...
Yeah, but often at the cost of complexity. You ended up in callback hell. The code flow became really hard to follow, and debugging was tough because you'd lose the clear stack trace that Java developers rely on.
So it feels like the whole history was about managing this scarce thing, the thread, rather than just focusing on the actual job you wanted done.
That's a great way to put it. The resource constraint shaped the programming model, not the other way around.
Okay, this is where it gets really interesting then. Virtual threads, VTs. This is the game changer from Loom. If platform threads were expensive OS resources, how on earth did Java suddenly make threads cheap? Like really cheap?
They basically decoupled the Java thread object from the OS thread. Virtual threads are a completely different implementation of java.lang thread, but they exist only within the JVM.
So the OS has no idea they exist.
None whatsoever. They're just Java objects. Creating one is just Instantiating a class, no expensive system calls needed.
Okay, but they still need memory for their stack, right? Where does that go?
Ah, that's the magic. It goes onto the Java heap, not the off heap, fixed size block like platform threads.
Onto the heap.
Yep.
So it's managed by the garbage collector.
Yes, and crucially, it's resizable. A VT only takes the stack memory it actually needs at any given moment. When it's done with the stack frame, that memory can be garbage collected like any other object.
Wow. So instead of a fixed megabyte, it's tiny.
Creating the VT object itself is just a few bytes. The stack grows and shrinks on the heap as needed. The difference at scale is just staggering. Sources showed tests where, trying to create maybe 100,000 platform threads would just crash with an out-of-memory error.
Right.
But you could spin up millions of virtual threads without breaking a sweat.
Millions of threads. Okay, but we still only have, what, 8, 16, maybe 64 CPU cores?
Yeah.
How do these millions of VTs actually run? That's the carrier thread concept, yeah.
Exactly. A virtual thread never runs directly on a CPU core. It needs to be executed by a good old-fashioned platform thread. We call these the carrier threads now.
Yeah.
The JVM manages a dedicated pool of these carrier threads, usually a fork join pool, sized roughly to the number of available CPU cores, so maybe one carrier per core.
The trick is how VTs use these carriers, the whole mounting and unmounting thing.
That's the core mechanism. When a VT is ready to run its code, the JVM mounts it onto an available carrier thread. It starts executing. But the moment that VT hits a blocking operation like thread.sleep or waiting for network I/O or a database called the JVM instantly unmounts it.
Instantly.
Yeah, it pulls the VT off the carrier. The VT's current state, its stack, is saved off to the heap, and that carrier thread, it's immediately free to pick up the next waiting VT from the queue and start running it.
Ah, I see. So the expensive carrier thread is never sitting idle waiting for I/O. It's always running some VT's code.
Exactly. Well, the VT that's actually waiting for the database or whatever is just sitting cheaply on the heap, consuming almost no resources until its I/O completes and it's ready to be mounted again.
That sounds incredibly efficient, almost too good to be true. There has to be a catch, right?
Yeah.
When does this unmounting process not work?
There is a catch. It's called pinned virtual threads. Pinning happens when a VT is in a state where the JVM simply cannot safely unmount it from its carrier thread.
Okay. Why would that happen?
The two big culprits are, one, if the VT's code enters a synchronized block or method. Two, if it makes a call into native code using JNI, Java Native Interface.
Right.
Also, object.wait.
So if my VT code uses synchronize for locking, and then inside that block it makes a database call.
Then that VT stays pinned to the carrier thread for the entire duration of that database call. The carrier thread is blocked, held hostage, unable to run any other VTs. It completely undermines the benefit.
Yikes. So heavy use of synchronized and blocking code is suddenly a performance killer with VTs.
A major performance killer. It's exactly the problem VTs were meant to solve.
How do you even find where this is happening in a big application?
Thankfully, the JVM gives you tools. There are VM options like jdk.tracePinned threads full or short. If you enable those, the JVM will log stack traces whenever a thread gets pinned for too long, pointing you right to the problematic code.
So you can then refactor away from synchronized, maybe use java.util.concurrent.locks, reentrant lock instead, which doesn't pin.
Exactly. Reentrant lock, stamp lock, other java.util.concurrent utilities are generally VT-friendly. Synchronized is the main one to watch out for in blocking contexts.
Okay, let's summarize the basics of using VTs. If I just want to run a task on a VT, what's the easiest way?
Dead simple. Thread.start, virtual thread, my runnable. That's it. Notice you don't even call .start, it just goes.
Nice. And if I'm used to ExecutorService?
The replacement is executors.new virtual thread per task executor, but here's the crucial bit. This is not a thread pool. Don't think of it like new fixed thread pool.
Right, because VTs are cheap.
Exactly. This executor creates a new virtual thread for every single task you submit to it. It fully embraces the thread per task model, which is now efficient thanks to VTs.
So, key rules for not using VTs or things to avoid.
Okay, three main things. One, never pool virtual threads. If you find yourself wanting to pool them, you've missed the point. They are meant to be created and discarded freely.
Got it. No pooling.
Two, don't use the VT executor to limit concurrency for accessing a resource, like a database connection pool. That's not its job. Use a semaphore for that. We'll maybe touch on that later.
Okay, use semaphores for limiting. And third,
avoid VTs if your tasks block very frequently, but only for extremely short durations, like microseconds. The overhead of mounting and unmounting, while tiny, can add up if it happens thousands of times per second for trivial waits. Platform threads might even be better in that very specific niche case.
Right, makes sense. Okay, so VTs give a scale, millions of sheep threads, but that sounds like potential chaos, right? Just threads everywhere with no coordination. This is where structured concurrency comes in.
Yes, exactly. Structured concurrency, or SC, is the second pillar. It's about bringing order and, well, structure to all this newfound concurrency. Think about normal code blocks like if statements or try-catch finally. They have clear entry and exit points, clear scopes. SC aims to bring that same structured predictability to concurrent tasks. It defines clear points where work forks into subtasks, and crucially, points where you must wait for those subtasks to rejoin, ensuring lifetimes are properly managed.
So unlike the old ExecutorService approach, where if I fire off 3 tasks and my main logic fails, those 3 tasks might just keep running indefinitely. Orphaned.
Precisely the problem. Unstructured concurrency leads to orphaned tasks, potential resource leaks, and unpredictable application state. SC prevents this. It guarantees that the lifetime of the child tasks is confined to the lifetime of a specific code block, the scope.
And the main tool for this is the StructuredTaskScope, right?
Yeah.
So it uses auto-closable.
Yes. StructuredTaskScope is the key API. You typically create it in a try with resources block, which leverages that auto-closable interface for guaranteed cleanup.
Okay, so what's the flow?
Inside the try block, you get your scope object. Then you use scope.fork task to launch your concurrent subtasks. These tasks usually run on VTs by default.
Forking tasks, okay.
After forking all the tasks you need within that scope, you call scope.join. This call blocks the parent thread, which is probably also a VT, until all the fork tasks complete, or until the scope decides to shut down early based on its policy.
Ah, the policy. That's important.
Crucial. Once join returns, or throws an exception, the try with resources block ensures the scope is closed. Closing the scope automatically handles canceling any tasks that might still be running, ensuring no orphans are left behind.
Clean shutdown.
Nice.
Let's talk policies. The source mentioned 2 main ones. Invoke all, like when you need data from multiple places.
Right, that maps to the shutdown on failure policy. Imagine fetching different parts of a user's profile. Their address, their order history, their account balance. You need all 3.
Okay.
You fork 3 tasks within a shutdown on failure scope. You call join. If, say, the address lookup task fails quickly with an exception, the entire scope shuts down immediately.
Ah, so it cancels the order history and balance lookups.
Instantly. It doesn't waste time waiting for them if one essential part has already failed. Then the code after the join would typically call scope.throw if failed to propagate that original failure. Saves resources, fails fast.
Makes sense. And the opposite pattern, invoke any, erase.
Exactly. That's the shutdown on success policy. Think of querying 2 redundant services for the same piece of data, maybe 2 different weather APIs. You only need the first successful response.
Right. Whoever answers first wins.
You fork tasks for both APIs within a shutdown on success scope. The moment the first task completes successfully, the scope shuts down, canceling the other, slower task. You then get the result from the winner using scope.result. It's a safe, clean way to implement races.
Okay, VTs for scale, SC for managing their lifetime safely. That brings us to the third piece, scoped values. You mentioned ThreadLocal issues earlier. Sounds like this is the fix, especially with millions of VTs.
It absolutely is. ThreadLocal's had, fundamentally, 3 big flaws that VTs just amplify massively. Let's recap them quickly.
Go for it.
1. Mutability. ThreadLocals were often static variables, and you could call .set on them from anywhere, changing their value unpredictably. Made reasoning about state very hard.
2. Leakage. We covered this. Forgetting .remove in pooled environments caused data from one request to bleed into the next. Nightmare.
Right. And 3, now super relevant with VTs, inefficiency via copying. When a traditional thread, or now a parent VT, spawned a child thread or child VT, the default behavior for inheritable thread locals was to copy all those values over to the child.
Copying, with potentially millions of VTs spawning children.
You see the problem. That copying overhead becomes astronomical. It could literally consume all your memory just duplicating these thread local values over and over again.
Okay, yikes. So how do scoped values elegantly solve all 3 of those problems?
They do it through 2 core principles: immutability and lexical scoping.
Immutability first.
With a scoped value, you don't set it whenever you want. You define its value for a specific block of code using a where method before that code runs. Typically looks like scoped value.where, mykaa, the value.run, an code that needs the value.
So the value is fixed for the duration of that run block.
Exactly. It's
Yeah.
effectively final for that execution scope. It cannot be changed from within the run or any methods it calls. This solves the random mutability problem completely.
And how does that help with the copying efficiency problem?
Because it's immutable. If the value can't change, the JVM doesn't need to copy it when passing it down to child VTs. It can just pass a reference, a pointer, which is incredibly cheap.
Yeah.
Problem solved.
Nice. Okay. And the leakage problem, the scoping part.
That's the other beauty. The value bound using where.run is only visible within the dynamic execution of that run block and methods called by it. The moment that block finishes, whether normally or via an exception, the runtime guarantees that the value is unbound.
Automatically unbound. No need for a manual remove.
None whatsoever. The lexical structure of the code defines the lifetime of the value. When you exit the scope, the value binding disappears. No leaks possible.
That sounds much safer. But what happens if you try to access a scoped value when it isn't bound, like outside the run block?
Good question. You'll get a no-sesh element exception. Because the binding is strictly scoped, you need to be sure it's available.
So defensively, you should check first.
You can use .isBound before calling .get, or more idiomatically, use the helper methods like .orelse default value to provide a fallback if it's not bound, or .orelse throw to throw a more specific exception. It forces you to handle the not bound case explicitly.
Okay, that makes sense. So bringing it all together, VTs, SE, scoped values, how does this change how we actually write concurrent code day to day? What are the new best practices or patterns emerging?
Well, the biggest shift is probably the return of the thread per task model. Remember how we said that was awful with platform threads?
Yeah, the create destroy overhead.
With VTs being so cheap that overhead is gone. So now, giving every logical unit of work, like handling one web request or processing one message its own dedicated thread, a VT, is actually the recommended approach.
Why? What's the benefit?
Clarity, simplicity. Each task runs on a clean slate. Stack traces make sense again because they directly relate to that specific task, not some random thread from a pool that ran 50 other things before it. Error handling and debugging become much more straightforward.
Okay, thread per task is back, but what about that scenario we touched on needing to limit access to a finite resource, like database connections? We used to use NuFix Thread Pool 5 for that. How do we do it now if we're using new virtual thread per task executor, which creates unlimited threads?
Great practical question. This is a key pattern. You absolutely do not use the VT executor to limit resource access. That mixes concerns.
Yeah.
Instead, you keep using executors.newVirtualThreadPerTask executor, so all your tasks get cheap VTs. But right before the code that needs to access the limited resource, like the database, you use a java.util.concurrent semaphore.
A semaphore, okay.
You initialize the semaphore with the maximum number of permits you want to allow concurrently. So new semaphore 5 if you only want 5 concurrent database operations.
Okay, then.
Before accessing the database, your VT code calls semaphore.acquire. If fewer than 5 permits are out, it gets one immediately and proceeds. If all 5 are already held by other VTs,
It blocks.
it blocks, but crucially, because it's a VT, it blocks cheaply. It gets unmounted from the carrier thread and waits on the heap until semaphore.release is called by another thread finishing its database work.
So the semaphore manages the resource limit and the VTs handle the waiting efficiently without hogging OS threads.
Exactly. It separates the concern of concurrency scheduling, handled by VTs, from the concern of resource access limiting, handled by the semaphore. It's a much cleaner model.
That is clean. Okay, and how are the big web frameworks adapting? Is it a huge migration effort?
Thankfully, no, the integration seems pretty smooth so far. In Spring Boot, for example, enabling VTs across the board for handling web requests is often just a single line in your application.properties.
Just one line.
Yeah, something like spring.threads.virtual.enabled, true. And boom, Spring starts using VTs for incoming requests, potentially boosting throughput dramatically for IO-bound apps.
And other frameworks, like Quarkus.
Quarkus takes a more opt-in approach, last I checked. You typically annotate specific JXRS endpoint methods with @run on virtual thread if you want that particular endpoint handled by a VT. Gives you more granular control.
Okay. And using things like completable future. Does that still work?
Absolutely. You can pass your new virtual thread per task executor to methods like completable future.supplyAsync, So the async task runs on a VT, or often you might find you don't even need completable future as much because simply starting VTs directly with thread.startVirtualThread gives you concurrency with much simpler synchronous looking code.
Simpler code, better performance. Sounds pretty good.
It really is a significant step forward for everyday Java development.
Okay, so let's quickly recap the 3 big wins from Project Loom we discussed. First, virtual threads. They give us incredibly cheap, plentiful threads, decoupling from the OS and solving the scaling bottleneck.
Right. Mass parallelism without the old resource costs.
Second, structured concurrency. Using StructuredTaskScope, it brings order to the chaos, managing the lifetimes of these potentially millions of threads safely, preventing leaks and orphans, and enabling clear patterns like fail fast or racing.
Safe, predictable management of concurrent tasks. And third, scoped values. The modern, safe replacement for ThreadLocal. They provide immutable, lexically scoped context propagation that's efficient and leak-proof, perfectly suited for the high concurrency world of VTs.
Exactly. Immutable, efficient, automatically cleaned up context. And yeah, while SC and scope values might still be technically in preview stages depending on the exact Java version, their design is fundamentally sound and solves long-standing problems. ThreadLocal won't vanish overnight because of legacy code, but the new way is just better.
It really feels like a paradigm shift. We've gone from developers obsessing over managing a scarce resource at the thread pool to a world where threads are abundant and managed safely by the structure of our code. The focus shifts back to the task itself, the business logic.
That's the core takeaway. So here's a final thought for you, the listener. If threads are no longer the bottleneck, and structured concurrency handles the complexity of managing them, what becomes the main challenge in designing highly concurrent applications now? Is it coordinating state across all these tasks, managing distributed transactions, or just grappling with the inherent complexity of the business domain itself now that the plumbing is less painful? Something to think about as you start exploring Loom.
Yeah, go try it out. See what happens when you can just spin up a thread for everything without thinking twice. It changes how you design things.
We'll see you next time for the next deep dive.